This video begins our look at assembly language, which will give us a sense of what happens at the hardware level when a program executes. Two key components of computer hardware are the CPU, or central processing unit, and the RAM, or random access memory. The CPU is where all computation actually happens. This is where things like your adder circuits and multiplier circuits are found. There are also a small number of units called registers that are used for storing values that are either being operated on or that are the result of an operation. There aren't many registers, so most of our data is stored in RAM, where there's lots of room to store things, but no computation actually happens there. So values have to be brought into the CPU if you want to work with them. Now, one thing that's worth noting, and that may not be obvious, is that our program instructions are actually stored with the data in RAM. And so what's going to happen is both instructions and other types of data are going to go back and forth between RAM and the CPU. Values get brought into the CPU in order to actually get operated on, and then results are written back. And then instructions are also brought in so that they can cause the appropriate pieces of hardware to operate. Like everything else in a computer, program instructions are stored as binary numbers using what is known as machine language. And each type of CPU has its own version of machine language. So you could imagine your program showing up as binary numbers that look like this, and they are in RAM, just like our data. When programming at this low level, it's easier to use assembly language, which is essentially human-readable machine language. It allows us to avoid having to figure out the actual bits that we need for a given instruction. So for example, if we want to read a value from the user and store it in the register R1, we can just write read R1 rather than having to look up and figure out that we need these bits to do that. We're going to use an assembly language for a virtual machine that was developed by the folks at Harvey Mudd. It's called the Harvey Mudd Miniature Machine. I'm going to call it HM-cubed. And in this machine, there are 256 memory locations in RAM. We're going to assume that the program occupies the initial location, so it starts at memory location 0 and works its way down. There are 15 general purpose registers in this machine. They're labeled R1 through R15. There are a couple of other special ones, but we can't use them in our programs. And there's more information and full documentation available here. Let's look at a sample program with 5 instructions. Again, we're assuming we start at memory location 0 in RAM. So we start by reading a value from the user, and that's going to cause the program to ask the user to enter something. Let's assume the user enters the value 6. That 6 is going to be read into register R1 because that's what the instruction specifies is the destination of this value. Next, we have a mul instruction, and this is equivalent to this Python instruction. So in this case, 6 is going to get multiplied by 6 to get 36, and then that 36 will get stored in register R2. Next, we have this instruction. We're saying take what's in R2, add it to what's in R1, and store the result back into R2. Next, we take what's in R2 and write it to the screen. And then finally, we come to this halt instruction, which stops the program. In general, the read and write instructions can take any register name R1 through R15 as their argument, and we're using RX as a placeholder to indicate any of those register names. We saw this add instruction in our previous program. It takes 3 register names. The first one is always where you're going to store the result, and the second and third are the operands of the addition. And we have similar instructions for all our key arithmetic operations: subtraction, multiplication, division, which is integer division, because we're only working with integers in HM-cubed, and then mod, which gives us the remainder of a division. 2 instructions that we haven't seen yet. One is called set n. It actually takes something other than a register. So you'll notice all of these other instructions that we mentioned only take registers as arguments. But set n, this n here, indicates that it takes an integer as its second argument. And that integer n can be anything from -128 to +127. And this allows us to assign a fixed integer to a register. And then add n also takes an integer and adds it to the current value of a register. Here's a second example program. Again, we start by reading a user input into R1. Let's assume we get a 7. Then we're using this set n to assign 2 to R2. Then we're using a div instruction, which is equivalent to what you see down here in Python. We're doing integer division. R1 integer divide R2, we get 3, we store the result in R3. Then we use add n to increase the value of R3 by 1. Then we write that final value of R3 to the screen, and we halt. So what this program did is give us the result of taking the user's input, dividing it by 2, and rounding up. Right? Because if we did ordinary division here, we would get 3.5, but it's been rounded up to 4. However, this version of the program doesn't work for even inputs, because if we trace through something like an input of 8, we're going to divide by 2 to get 4, but then we're still going to add 1, even though we don't need to get 5, and then that's what will be produced as the output. To make the program work for even inputs, we need 2 additional instructions that you see here in gray. Let's trace through it on an input of 8. So the 8 gets read into R1 as before. We again store 2 in R2. We divide R1 by R2 and store it in R3. But this time we're also using the mod instruction, and it's going to do R1 mod R2, which gives us 0, and that is stored in register R4. And then we have this JEQZ, which is short for jump if equal to 0. And it says that if the contents of whatever register is here, so in this case R4, are equal to 0, then jump to the line number given as the second argument, which in this case is 6. And because R4 is equal to 0 in this case, we're going to jump to line 6. We're not going to do line 5, which means we won't add 1, which was the problematic part last time. We're just going to write the current value of R3, which is indeed 8 divided by 2, and then we're going to halt. If we have an odd input like 7, we read it into R1, we store 2 in R2, we do the division, which again is integer division, and this time when we do the mod, we're going to get 1 because 7 mod 2 is 1, and that gets stored in R4. And so when we come down to our JEQZ, because R4 is not equal to 0, we're not going to jump. We're still going to do line 5, which is going to round up, which is what we want here, and we're going to write the 4 and halt.